Hello friends, the topic for today is 8254 modes of operation. As per the feedback received from students, I am uploading this new video for more clarity on this topic. 8254 is a counter timer device which is used for timing control applications in microcomputer based systems. It has 6 modes of operation. We are going to discuss these 6 modes of operation with the help of timing diagram. Let us start with the presentation. Let us start with the presentation. The topic for today's presentation is 8254 modes of operation. Welcome to our channel Engineering and Technology for You. If you are not subscribed, kindly subscribe and press the bell icon. Let us start with the introduction. Now, 8254 is a counter timer device. It is programmable interval timer. It is designed to solve common timing problems in microcomputer system design. It has 3 independent 16-bit counters, counter 0, counter 1 and counter 2. And each is capable of handling the clock frequency up to 10 MHz. The operation of the counter is in the down mode. So when the count is loaded into the counter, it will start decrementing. So the counting is in the down mode, and the count can be BCD or hexadecimal. Here the counter is controlled by loading the count to the command word register. We can load the count into the command word register even when the counter is running. So that's why it is called on the fly reading. It supports on the fly reading. There are 6 modes of operation. All modes are software programmable. So let us see the block diagram and pin configuration before we go into the details of the modes of operation. Here, as you can see in the block diagram, we have counter 0, counter 1 and counter 2. These are the 3 counters which are independent and identical. They are 16-bit. And each counter has got 3 signals. 2 are inputs, clock and gate. These are the inputs to the counter, and this is the output signal out. So similarly for clock 1, here counter 1, it will have these 3 signals, and for counter 2 it will have these 3 signals. Then on this side we have the data bus buffer that is connected to the data bus D0 to D7, and we have the read write logic with the signals read bar, write bar, and these address lines A0, A1, which are used for selecting the counter, and chip select for selecting the chip. And we have the control word register where the control words and the count is loaded, and then the count will be loaded into the counter. Let us see the pin diagram now. So if you look at the pin diagram, we have the data lines D0 to D7, and then the 3 signals for counter 0, clock, out and gate. Similarly, out, gate and clock for counter 1, gate, out and clock for counter 2. Then we have the 2 address lines A0, A1, and these are the signals of the read write logic, VCC and ground. So we'll not discuss the details of these signals. Already it is covered in the previous video. Now let us see the counter timer functions. See, these are the common functions in microcomputer system, and they are implemented with the 8254. First function is the real-time clock. So the real-time clock can be implemented with the help of 8254 by taking a delay for the 1 second and then counting up to 60 and so on. Then we have the event counter and digital one shot. There is a mono shot or one shot multivibrator. Then we have the programmable rate generator and square wave generator. These are the generators which will divide the input, say using the counting. Then we have the binary rate generator, rate multiplier, and we have complex waveform generator and complex motor controller. So these are some of the applications which are implemented with 825. Now how to implement these applications we'll come to know when we actually go through the different modes of 825. So modes of operation. Now here mode 0, it is called as interrupt on terminal count. It is typically used for event counting. So after the terminal count, the out signal will be high, and that will be used for interrupting the device. Then mode 2, it is hardware retriggerable one shot. So in mode 1, the counter functions as a retriggerable monostable multivibrator or one shot. Then the next mode is mode 2, that is rate generator. Now this mode functions like a divide by n counter. So the input is divided with the help of the counter. Then mode 3, that is square wave mode. So this is generally used for baud rate generation. Then mode 4, we have the software trigger strobed. So now here the counting sequence is triggered by writing an initial count. So that's why it is called as the software trigger strobe. Then the last mode is mode 5, hardware trigger strobe. Now in this mode, counting is triggered by a rising edge of gate signal. So the gate pin is used here. That's why it is called as the hardware trigger strobe. Now the initialization procedure for each mode is almost same. We'll have to follow the same procedure for each mode of operation, but the output for each mode will be different. So the steps necessary are, say, first we have to write the control word into the control register. So as per the mode, we'll have to find the control word. So that details are covered. Then after that, once we write the control word into the control register, then we have to load the count value in count register. So the count value, there are two options, BCD and binary or hexadecimal. So as per the mode of operation, we can load the count value. Then modes of operation. So here the count value depends on the control word. So there are three possibilities. If the control word is framed for writing the least significant bit only, then only the LSB is written alone. Then if the control word is framed for writing MSB only, then only MSB is written. So these two are the 8-bit modes, and the third mode is writing LSB first and next MSB next. So this will write the LSB first and then MSB, that is, it will load the 16-bit count, and this 16-bit count, either it can be a hexadecimal or BCD. Then in all the modes of gate acts as a control signal to start, stop, or maintain the counting process. So when the gate signal is high, the counter is enabled, and when the gate signal is low, at that time the counter is disabled, so it will stop counting. In this way, the modes of operation are set as per the requirement, and the count is loaded. Then to understand, we'll use the timing diagrams. So there are conventions which apply to all the mode timing diagrams. First is, counters are programmed for binary, not BCD. So whatever timing diagrams we are going to see, so here we are programming for binary operation, and the count will be, say, particularly in binary, or in other words it will be in hexadecimal, and reading writing least significant byte only, LSB only. So it will be 8-bit count only. Then the second, the counter is always selected, so CS, that is the chip select, is always low. Then control word, CW stands for control word, and CW is equal to 10 means the control word of 10 hex is written in the counter. So that will define the different parameters and the mode of operation. Then LSB stands for least significant byte of the count, and the last numbers below diagram are count values. So here the lower number is the least significant byte, so that will be important for us, and the upper number is the most significant byte. And since counter is programmed to read write in LSB only, the MSB or most significant byte cannot be read. And say N stands for a count. Vertical lines show transition between the count value. So when we actually see the timing diagram, then it will be clear to you. Then let us go to the first, mode 0, interrupt on terminal count. So typically it is used for event counting, as we have already discussed. Then here we'll have to load the control word, and when the control word is written, the out signal is initially low, and it will remain low until the counter reaches 0. So the counter is loaded with the count, and the counting will start by decrementing the counter. So when the counter reaches 0, then at that time the out signal is goes high and remains high until new count or new mode of control word is written. Then here the gate is used for enabling and disabling counting. So if gate is equal to 1, will enable counting, gate is equal to 0 will disable counting. It has no effect on the out. Then let us see the timing diagram for mode 0. So first timing diagram, here first we'll load the control word, Now control word for mode 0 with LSB only, it is 10, and the count here we are taking it as 4. So this is on the when now WR bar, it is active low signal. So when it goes low, the count control word will be written, and similarly the count will be written in the counter. So this is the clock signal and this is the gate signal. Now here the gate is high and this is the out signal. So these are the three signals for the counter. So initially the out will be high, and when we load the control word, it will go low. Then after that we are loading the LSB is equal to 4, the count. So when the count is loaded, after that the next cycle, the next clock cycle, here we are loaded the count 0, 4. This is the LSB, the count. This is the MSB. So now here when it is loaded, then the counting will start. So it will be decrementing. So 4, 3, 2, 1. Now at this age, it is reaching 0. So once it is reaching 0, the out signal will become, or it is asserted, and it will remain high. The counting is still going on. So after 0, if you decrement, you will get FF, then you will get FE. In this way, the counting will be done. So the clock pulse does not decrement the count unless it is the count is loaded properly. So for n plus 1 clock pulses, the after the count is written, then we'll get this high. So you can see here, this is 1 pulse, then here we'll get it n plus 1. So after 5 pulses, we will get this as, here it is changing to 0. So as soon as it becomes 0, it will be high. This pulse plus this 4, like this, get n plus 1. Then let us go further. Mode 0 timing diagram 2. Now here we are taking the case with the gate signal. So already we have discussed that gate is equal to 1 will enable counting, gate is equal to 0 will disable counting. So again, let us see the diagram. So the control word is written here, that is 10, and the count LSB is written here. Now after this, the count, the next pulse, the count will be here. You can see at this. So the count 03 is loaded into the counter, and at that time, now here the gate is high. Here the gate becomes low. Now the counter is decremented by 1. Now the value becomes 02. Now as the gate is low, the counting will be disabled. So you'll get 02, 02, 02 here. Then here the gate is made high. So the counting will start. So it will become 01. And then when it becomes 00 here at this point, the out signal will become high. So with the help of gate, we can disable counting. And so the interrupt on terminal count, so the terminal count will be delayed because we have delayed the we have made the gate low for this period. Then let us go to the next timing diagram. Now here we are considering new count. So if new count is written to the counter, then it will be loaded on the next clock pulse and the counting will continue from the new count. Let us see how we can do it with the help of timing diagram. So first we are loading the control word, that is 10. Then we are loading the count, LSB is 3. So you can see here the count is loaded. Here it is undefined. And the gate signal is high throughout. And out signal, it is high initially. And then when this is loaded, it will become low. And at this point, the counting will start. So 0, 3 will be decremented to this 2, then 1. Now at this point, we are loading another count. So the count is loaded again. So it will read on the fly and you can see the counter will have the value. Then again it is decremented to 1, and when it becomes 0 at this point, the out signal will be, and then it will be used for interrupting the devices. So this is the case where we are loading the new count, and as per the new count, the counting will continue from the new count. Then let us go further. There is mode 1. So this is hardware triggerable one shot. So in mode 1, the counter function as a retriggerable, monostable or multi-stable multivibrator one shot. So again out will be initially high and out will go say on the clock pulse following the trigger to begin the one shot pulse. So here the one shot pulse will be a low pulse. So during the one shot pulse, the out will remain low until the counter reaches 0. Then out will then again go high and will remain high until the clock pulse after the next trigger. So this is how the mode 1 will work. Let us see with the help of timing diagram. So here you can see, after writing the control word and initial count, so you can see here the control word is written and here the count is written. Again the count is 3 here. Now control word is 1, 2 now. It is not 1, 0. It has changed because the mode has changed. And this is the clock. Now this is the gate. A gate will be used as a trigger. So it will give us a pulse, a high, say low to high, and then again high to low. So it will generate a pulse. Now when this count is loaded, it will be loaded into the counter. You can see here. When it is loaded, the out signal will be low, and then it will remain low till the count becomes 0. So at this point, the counter is becoming 0. Then it will become high. So this is the period of the mono shot. I hope you are following. Here, say the one shot is retriggerable. So again, we can retrigger it with the help of gate. Now again, when we retrigger it, again the count will be loaded and this out will become low. And then again the count is decremented 3, 2, 1, 0. And then again it will become high. Out will become high. So in this way it will work. Then let us go to the next timing diagram for mode 1. So here in this case we consider the new count. So let us say the control word is written 1 2, and then we write the count. Now in this case the count is 2, and then we write the new count, that is 4. This is the clock signal. So here we are giving the trigger. As soon as we give the trigger, now the count is 0 2, and the out signal will become low. Then it is decremented, it will become 0 1, and then when it becomes 0 0, here you can see this edge will become high. Then again we have loaded another new count, that is 4. So in the on the next trigger, when we give the trigger, the count 0 4 will be loaded, and then again it will be decremented to 3 2 1 and 0. Again this out will become. So in this way we'll get a low pulse. This is called as the one shot. So the one shot pulse continues until the new count expires. Then let us go further. Mode 2, that is the rate generator. So it functions like a divided by n counter. So the input will be divided by the count, that is value which is the count. So we take it as n. It is typically used to generate real-time clock interrupt. So out will be initially high, and initial count has decremented to 1. The out goes low for 1 clock pulse. Initially the out will be high, and it will go low for only 1 pulse, 1 clock pulse, when it is decremented to 1. Then again it will become high, and the counter reloads the initial count and process is repeated. So that's why here the process is repeated. That's why mode 2 is periodic, and the same sequence is repeated indefinitely. So for initial count n, the sequence repeats every n clock cycles. So that's why we call it as the rate generator. Let us see with the help of waveform, timing diagram or wave. So here we are loading the control word. Now control word has changed to 1 4 for the mode 2, and then the count is 3. This is the clock. So after writing the control word and initial count, the counter will be loaded on the next clock pulse. So you can see here it is loaded at this 0 3. Then it will be decrementing, so 0 3 0 2 0 1. So when it becomes 1, at that time it will give us a low pulse. Then again it will become high, and again it is loaded. The count is 0 3 0 2. When it becomes 1, again we get low. So this will be repeated. So again 0 3 0 2 0 1, and again low pulse. So that is a periodic signal. So this is the rate generator. Then let us take the case when gate is used here for enabling and disabling the counting. So here again the control word is loaded and the count is loaded, and the gate, it goes low during the output pulse. Then the counting will be disabled. Let us see. Here you can see the LSB is equal to 3. This is loaded into the counter, and then counter is decremented. Now once it is decremented, the gate becomes low, so the counting will stop. we will get 0 2 here. Then again the gate is made high. So now instead of with the same 0 2, it will not decrement, it will load the same count, that is 0 3. Then it will become 0 2 0 1, and once it becomes 1 at this point, this will get the loop. So the waveforms 1 and 2, they are similar, only here we are added the gate input, it is disabling the counting. Then let us go further. Now we'll consider the third type of wave timing diagram where we make use of the new count. So first we load the control word, it is 14, then the first count is 4 and the next count is 5. Let us see how it will operate. So once we load this count, now the counter is loaded with this 0 4, and the out signal is initially high, and it will start now counting. So it will become 0 3 0 2, and when it becomes 1 at this point, it will give a loop. But we have loaded this new count at this point. So this count will be loaded here in the counter, and then this will be decremented. So it will become 4 3 2 1. Again we'll get the low pulse. So in this way the counter will be loaded with the new count on the next clock pulse, and counting will continue from the new. Okay. Then let us go further. Mode 3. So this is the square wave mode. So it is used for baud rate generation, as we already discussed, and it is similar to mode 2, except here the duty cycle will be exactly 50%. If the count is even, then it will be 50%. So output will be initially high, and when half of the initial count has expired, the out goes low for the remainder of the count. So for half of the count it will be high, for next half it will be low. So again mode 3 is periodic as the mode 2, and the sequence is repeated indefinitely. So it will give us a square wave of period n clock cycle depending on the value of. So let us see the timing diagram. So again here now the control word has changed to 1 6, and the count we are taking even count, that is 4. So this is the clock, and gate is high throughout, and the out signal initially it is high, and when the count is loaded, here you can see 0 4 is loaded, and then the counting will decrement. So it will directly go to the 0 2, and it becomes half, so the out will become low. Again it will have the 0 4 and 0 2, so it will be low during this period, then again it will be high, again it will remain high for the same period, then again it will be low. So this way it will generate. So this allows counter to be synchronized with the software, and it will generate. Then let us go to the next timing diagram for mode 3. So here we'll make use of the gate. So the count control word is 16 and the count is 4. So gate, now here the count is loaded 0 4, so it will be 0 2, and then again this will be low for this period, Now here the gate becomes low. So now the counting will stop. That's why this after this will become high, and here it will continue to be high. Then again, when the gate is high, again it is loaded with 04, and then it will remain high for these 2 periods of the clock, and then it will become low when it is half, and we will get the low part of the. So if the gate goes low while out is low, out is set high immediately. This is not shown in the timing diagram. So no clock pulse is required. So trigger reloads the count with the initial count on the next clock pulse. So gate input can be used to synchronize the counter. So we can synchronize the counter with the help of gate. Then let us go further. So that is the third case, that is the new count case. For this we are not going to use the timing diagram. Let us understand it. So writing here, if the trigger is received after the writing a new count but before the end of the current half cycle of the square wave, the counter will be loaded with the new count on the next clock cycle, and counting will continue from the new count. So as soon as you load the new count, from the next clock pulse, the counting will continue from the new count. The new count will be loaded at the end of the current half cycle. So if it is received after writing the new count but before the end of the current half cycle, then it will go to the next clock pulse. In this way it will work. Then let us go to the mode 4, software trigger strobe. So here we'll be making use of the count as a trigger strobe. So out will be initially high, and when we load the initial count, then when it expires, the out will go low for 1 clock pulse, and then it will go high again. So count here, the counting sequence is triggered by the writing the initial count. So as per the count, the triggering will be. Let us see with the help of. Now the control word, now it is 1-8, and the count is 3, and here this is the clock, this is the gate is high, out is initially high. Now here the counter is loaded with 03, then the counting will start 02, 01, and here it becomes 0. So when it becomes 0, we'll get a low pulse. So after writing the control word and initial count, the counter will be loaded on the next clock pulse, and initial count n, out does not strobe low until n plus 1 clock pulse. So you can see here, this strobing will be, it will go low only after this meaning clock pulse, n plus 1 clock pulse. So then let us go to the next timing diagram. So that is the gate case. Gate 1 will enable and gate 0 will disable. Let's see how it will. So in this case, we are taking the count control word as 18 and LSB count is 3. Now in this case, the gate is low initially. So after loading the count, the counting will not start because the gate is low. So you can see 3, 3, again 3 here. So here the gate becomes high. At this point, the counting will start. It will become 2 and 1. And once it reaches 0, we'll get a. So the gate will disable the counting when it is. So during this period, when the gate is low, the counting is disabled, and it will be enabled only when it is high. You can see here 3, 2, 1. Here it is, the counting is. So, but the gate has no effect on the out signal. Immediately, when the gate is high, the out signal is with respect to the count. So unless and until it becomes 0, it will not go. Then let us go further. Timing diagram 3. Again, now this is the third case, that is the new count. In this case, the control word is 18. The first count is 3, second count is 2. This is the clock, this is the gate, is high throughout. Initially out is high, and the count is loaded here. So the counting will start 3, 2, 1. Now once it becomes 1, now again we are loading another count, new count. So this 2 will be loaded, and then again it will be incremented to 1, and when it becomes 0, then only we'll get this. So this is how the software trigger strobe, it is mode 4, will work. Then let us go to the last mode, that is mode 5. It is hardware trigger strobe. So the out will be initially high as usual, and counting is triggered by rising edge of the gate, because here it is the hardware trigger strobe. So we'll have to trigger with the help of the gate signal. So when the initial count has expired, out will go low for 1 clock pulse and then go high again. So it is similar to mode 4. Now only the triggering has changed. Now it is to the gate. Now trigger results in the counter being loaded with the initial count on the next pulse, and the counting sequence is retriggerable. So the out will be not strobe low for n+1 clock pulses after any trigger. So it is the other things are same as mode 4. Let us see with the help of waveform. Now here the control word is changed to now 1A. That is for mode 5, and the count is 3. So after writing the control word and initial count, the counter will not be loaded until the clock pulse after a trigger. So here you can see the gate trigger is here, then only the counter will be, and then it will start counting 3, 2, 1, and once it becomes 0, we'll get a low pulse, and then again we are triggering at this point. Then again the same count is loaded, and again you will have the count 3, 2, 1, 0, will get a low pulse like that. So in this way it will continue. Then the next timing diagram for mode 5, it is for the new count. So if new count is written during the counting, the current counting sequence will not be affected. If the trigger occurs after the new count, then it will be written here in the counter. Counter will be loaded with the new count on the next clock pulse. Let us see. The control word 1A. The first count is 3, second count is 5. This is the clock, and here we are triggering with the help of gate pulse on the gate. So after this we get the count in the counter. The out will be initially high, and here the counting will start 3, 2, 1, and here at this edge becomes 0. So we'll get a low pulse, and then we have loaded the new count 5. So now the new count will be loaded here after this trigger pulse, and again it will now decrement 5, 4, 3, 2, 1 and 0, and we'll get a, in this way toolbar. So with this, we come to the end of this video. If you have any queries, you can put it in comments, or you can ask on the my Facebook account, Twitter, Gmail, or Instagram. Then if you like the video, press the like button and share with your friends. So this is a very difficult topic, and almost textbook it is not given properly. Then subscribe to our channel, Engineering and Technology for You. Then use the bell icon to get the notification for future video. Then thanks for watching. Also, you can use the Intel datasheet on 8254.